And we're on. So as I was saying, yesterday we were talking about how the problems that we work with, that frequently we're applying the same kind of logic to many different situations. And depending on the situations, the formulas that we use, they accomplish the same thing, but they make accommodations to whatever the particular situation is. So I'm going to start with the simplest version of what we might encounter in those kinds of situations. So for instance, let me just make sure I got this working. Okay, so for instance, let's say I want to discuss, I'm going to move this over. Let's say I want to discuss, I want to calculate confidence intervals. Right? So let's talk about confidence intervals. We can have two kinds of confidence intervals, can't we? We can have confidence intervals of a mean, and we can have a confidence interval for a proportion. And our confidence interval represents the range within we expect the mean to fall. So for instance, if we have a population and we sample 25 people from that population, and we find that the average weight for those 25 people is 150 pounds, and the standard deviation for that population, that sample of 25 people, is 25, right? We want to say to ourselves, okay, well, I have a mean that approximates, I think, or is intended to approximate the mean of the population. Um, how confident am I that it's really 150? Well, that's hard to predict, but what I can do is I can say to myself, well, given this information, what's the probability, what's the range of values that I can be 95% confident that the real mean falls within? Well, let's talk about this for a second. If I know the population standard deviation, it's a little unusual to know that because you'd have to sample the entire population. But if you knew the standard deviation of the population, and you knew that the standard deviation of the population was indeed 25, right? That it really was 25. Well, the confidence interval is going to be the mean plus or minus, say I don't know the actual population mean, but I know the population standard deviation, plus or minus 1.96 times the standard deviation. Excuse me, not times the standard deviation, but times the standard deviation for every sample of size 25 that you might take from this population with a standard deviation of 25. Well, what is that standard deviation for the repeated samples? That's called a standard error. And that standard error is equal to standard deviation of population over the square root of sample size. So this is always going to be smaller than the standard deviation for the population. So that's going to be equal to, let's see, 25 over the square root of 25. It's going to be equal to 5. So our standard error is going to be equal to 5. So 1.96 times the standard error, okay, or in other words, plus or minus 1.96 times the standard deviation of the population over the square root of n is going to be, I'm going to round it off to 2 times 5. It's going to be equal to 10 in our case, right? So now my mean was 150. So my confidence interval is 150 plus 10 and 150 minus 10, or in other words, 140 to 150. On the test, of course, you're going to use 1.96 instead of using the 2 that I used here just to get through this very quickly. Okay, so I think we know that pretty reliably. So now the one of the things that might be a problem here is that, well, we all frequently don't know the standard deviation of the population, so we have to rely on the standard deviation of the sample to approximate the standard deviation of the population, just as we use the mean of the sample to approximate the mean of the population. Okay, so in that case, we've introduced an extra layer of possible error here, right? Because we don't know that really is. There is some chance that's going to be bigger or smaller than that, right? So instead of relying on this the same way as thoroughly as we would if we knew the population standard deviation, we are, instead of using 1.96, we're going to use a larger number so I get a wider confidence interval to adjust for that extra uncertainty. Okay, and that larger number is going to be, instead of being the z-score for 95% of the possible outcomes for the sample of size 25, which is where that 1.96 came from, it's going to be a t-score. A t-score we're going to get from a table. So now, if I were relying on standard deviation of the sample, it'd still be standard error, would still be standard deviation over the square root of n. It's going to be equal 25 over 5. It's still going to be 5, since that's what I got here. Okay, plus or minus, it's going to be plus or minus. It's going to be plus or minus the t-score that I need for 95% confidence interval, right? And that t-score is dependent on the sample size. And I'm going to go quickly to, as quickly as I can anyway, to a t-table. Here's the one that's it. I think this one happens to be in another book. Let me get rid of that thing. Okay, so the way we figure out what that t-value has to be, is we look for a 95% confidence interval, which also represents 2.5% in either the left, in both the left and the right tail of the normal distribution. So I'm going to use this column here. Okay, and if I scroll down to 25, I don't actually use 25, right? Because this column doesn't represent the sample size, it represents the degrees of freedom, which is n minus 1. So 25 minus 1 is going to be 24. So the value I'm going to use there, instead of 1.96, is 2.06. So I'm going to go back here. I'm going to put plus or minus 2.06 times the standard error, which is 5, and this is going to come out to 150, right? Minus 2.05, 10.12, and 150 plus 10.12. So our confidence interval then is going to be 139.88 to 160.12. Okay, it's going to be a little bit different than what we got before, because we have that extra wide interval. This should have been 160, excuse me. Right, instead of 140 to 160, it's going to be a little further out in each direction. Okay, so that's the way we would handle confidence intervals, and when we would decide to use the t-score, the t-value, instead of the z-value. Okay, now look at how this t-value increases with the sample size. Small sample size suggests a lot of error in the calculation, in the assumption about our standard deviation of the population. So the correction that the t gives us is quite large, 2.3, 2.5, and so on and so forth. But as our sample size gets larger, it becomes more and more reliable. If it's an infinite sample size, well, it's our 1.96, the same as the z-value that we would use. So instead, we have to look through, up to a certain point, we have to look through this table for a t-score. But if the sample size is very large, infinite in best case, the entire population, we wouldn't need to use this. But if we set a cutoff of, say, 30, well, anything above 30, we're already down very close to 2. So very frequently we'll say that if the sample size is greater than 30, then we'll be satisfied with using the z-score instead of the t-score. In other words, 1.96, and not bother to go to the t-table to look up that value. Okay, so let me just ask you a quick question. Is that clear so far? Anybody have any issues with that? I'll wait for a response so I know that you guys can hear me. Okay, good. Thank you. So, okay, so that's how we can do with confidence intervals. Well, there's a twist on confidence intervals, isn't there? Sometimes we deal with proportions. I'm going to move over to another clean sheet of paper. And in the case where we're dealing with proportions, we might have another kind of sample. I'm going to say, let's say again, we have a sample size of 100. Out of those 100 people, we find that, let's say 12 people are diabetic. So our proportion in that sample of people in this sample that are diabetic, P, I'm going to call it P cap, because just like I use X bar, I'll use P cap to represent the sample mean, the sample proportion, is equal to 0.12, right? 12% of the population is diabetic, or 12% of this sample is diabetic. Well, I'm not really interested in the proportion of the sample that's diabetic. I'm interested in the proportion of the population that's diabetic. Okay, so we're interested, well, what is that? Well, just like the mean, this value approximates my population proportion, right? But since I need a handle on how accurate that number is. So again, I'm going to employ the 95% confidence interval to find out what that is. Well, just as before, the way that I do that is I'm going to say my population, my sample proportion, plus or minus my a value that I'm going to use here to represent 95% of the outcomes of repeated samples this size, to represent the that range that I would need to capture the mean 95% of the time. So I'm going to say population proportion plus or minus 1.96. Now notice this is a large sample, right? It's a sample size of 100. Any proportion problem that you're going to get is likely going to include a large sample size. So I don't think you're going to have to worry too often about the t-score here. I think more frequently you'll be working with larger samples like this. One rule, though, is that the proportion, the size of the group in either one of these situations, in either one of these possible outcomes, diabetic or non-diabetic, the sample size should be larger than 5 for each side of that possibility. So in other words, we have 12 people that are diabetic. That means we had 88 here that weren't. So both of them satisfy the rule that we have to be greater than 5 on either side for this to work. Okay, so we have the population proportion, the sample proportion, plus or minus 1.96 times the standard error. Well, now, how do I calculate standard error for proportions? Well, I'm going to calculate it using this formula. Standard error is equal to the square root of the proportion of successes, diabetic, times 1 minus p, the proportion of the rest of the population, over n. So in this particular case, it's going to be equal to 0.12 times 0.88 over, sample size was 100, and then I'm going to find the square root of that. Okay, so that's going to be my standard error. Let me do it real quick. Let's go ahead and solve this. 0.12 times 0.88 times, 0.12 times 0.88 equals, divided by 100. It's going to move the decimal place over, and we're going to find the square root of that is equal to 0.032. I'll round that for my purposes to 0.03. Standard error is equal to 0.03, so it's going to be 1.96 times 0.03. Again, for my purposes to do this quickly, I'll just round it off. So the 95% confidence interval for P, for the population proportion, is going to be equal to 0.12 plus or minus approximately 2 times approximately 0.06, 0.06. So it's going to be between 0.06 and 0.18. Okay, so we pretty much covered most of the possibilities that you're going to get in that kind of thing. The problems might be a little bit more complicated, and very frequently the information that you need is going to be buried within some narrative that puts it into a public health perspective. They'll give you a description of the population and so on and so forth. One of the real problems here is parsing the information that's in the problem to pull out the numbers that you need, not get confused with extraneous information that might be in the description of the problem. Okay, so that you're going to have to practice a little bit, and it can be a little challenging every once in a while. But if you're patient, you'll see where the information is that you're going to need. Okay, so now let's move on to another a little bit more complicated application of this stuff, but really using the same strategy. First, sampling a population, and then using that sampling information to predict how other samples or all samples of that size would likely perform, and using that to distinguish between one population and another population. Same offshoots of the same formulas, the same kind of calculations, but for a whole new purpose. Okay, so let's move on to this. The first version of this that I'm going to bring up is a single sample t-test. Okay, we want to compare the means of two populations. One of the ways that we might do that is to uh, uh, sample. Let's say that we know, for instance, that the mean. I keep running into. I keep having the same things pop into my head. Unfortunately, I was hoping to give it a little bit more variety. Let's say that the mean mean top speed for American cars, mean top speed for American cars is equal to 110 miles per hour. And the mean top speed for European cars, many of which are sports cars, is is unknown, right? Now we go to Europe, we sample 25, sample size is 25. We sample 25 randomly selected European sports cars, and we find that the mean for the speeds, top speeds of those European sports cars is equal to 120 miles per hour, make it 125 miles per hour, and that the standard deviation for the for those cars is, let's say, let's make that let's see, 5. Let's make that 100 miles per hour. Excuse me, 10. Should I make it 10? Let's see, 5, 2. Say I'm gonna pick. I want to pick a number out that'll work well with here. 5 into 2. And that's gonna be enough. Let's say it's 25. The standard deviation for for these samples are 25. Okay, well, let's go back here and let's say that instead of looking at this, let's say that I knew that the standard deviation for all European sports cars was known to be 30, was known to be, let's say, 16 miles per hour. Okay, let's say that it was known to be the case. Okay, so now if I wanted to compare a known mean of 110 miles per hour to another situation I think is a different population, a group that has a different mean, right? Well, I want to compare these two. I have a single sample, right? And I'm comparing it to a known value. Okay, so let's see how this distribution would look. My mean is 125 miles per hour. I'm going to actually draw this. What would my samples, repeated samples, look like, presumably? Well, the mean would be 125, right? And the sample size, the standard deviation or standard error for repeated samples from this population, right, would be, if it's known, it would be 16. So what's my standard error going to be equal to? Well, my standard error is going to be equal to 16, is going to be equal to a 16, my standard deviation, over the square root of my sample size, which is 25. 16 over 5 is going to be equal to approximately, I'm going to call it 3. Okay, so my standard error is going to be equal to 3. So I would expect that two standard deviations below 125 is going to be something around 119, and two standard deviations above 125 is going to be about 131. Okay, that's with a known standard deviation for this particular other population. Okay, so now in that case, if I take this sample, if this sample that I took got a mean of 125, here we are, and I know the population of American cars, the entire population of American cars is 110, how likely is it that I would get a value of 110 out of this population? How likely is it that that these two populations could be the same? Well, you can just see intuitively that 110 is so far away that the probability that you would get a result of 110 from this population is very, very, very tiny, right? And we're gonna calculate what that probability is. And the way we calculate that is we calculate what the z-score for that number has to be. So what's the z-score for 110, right? Given that the mean, excuse me, for what's the probability? I could do it either way, but I'm going to say what's the probability that we get a mean of 125, right? Difference between 125 and 110, right? In other words, I'll put the formula down here. X minus mu over the standard error. How many standard errors or standard deviations for means are we apart? X is 125 minus 110 over the standard error. The standard error is going to be equal to, we've calculated it, standard deviation over the square root of the sample size. That was going to be equal to 3 in this case. Okay, what's the probability? How many z values apart are these? Well, it's going to be equal to 15 over 3, so that's 5. So we know that we're not even going to find that value 5 on the z table. The probability is going to be less than 0.001. Well, let's say that it came out, let's say this was really something like 3 and it came out to be 0.001. We almost always do double-sided t-tests, right? Two-sided t-tests. So I would take this p-value that I get from the C table, which shows one corner of the normal distribution. I would multiply it by 2 to get a double-sided outcome. So my p-value two-sided, right? P-value two-sided is going to be equal to 0.002. Well, we are satisfied to say that these two means for these two populations are not equal if we can rely on the fact that we'd be wrong less than 5% of the time. In other words, have a 5% chance of error or have an alpha of 5.05. Okay, so in this case, our probability of these two from being from the same population is well less than 0.05, right? So I can say that they're not from the same population. Their means are not the same. Okay, now to take a step back, very often when we do studies, we want to postulate what our object is in doing that study. Okay, so let's at the beginning of this, you might consider, instead of just going through this calculation, stating an outcome that you're intending to prove. And the way we do that is hypothesis testing. Okay, I'm going to propose two hypotheses. H null, okay? In other words, the hypothesis that there's no difference between the two of these. Okay, in that case, I'm going to say that's going to be equal to the mean for American cars is equal to the mean for European cars. Okay, my alternative hypothesis is that the mean for American cars does not equal the mean for European cars. American cars, we knew the mean in this particular case. That made it a single sample t-test because I didn't know the true mean for European cars. I had to base it on my sample, right? So that's a single sample t-test. Well, now also the other thing is I keep using the term t-test, yet I used the z-score. Reason I used the z-score was because I knew the population standard deviation. Had I not known the population standard deviation, I would have had to rely on the sample standard deviation that I calculated from these 25 numbers. Well, let's see what would have happened then. First of all, I can't use the t-value, the z-value. I have to use the t-score for that sample size. Okay, so now let's see. How would I apply that? Well, I'd apply it basically the same way. My t-score, right, is equal to my sample mean minus my population mean over my standard error. Well, my standard error in this case is going to be standard deviation of my sample, because I don't know it was different, 25 over the square root of my sample size. 25 is equal to 5. So in this case, my standard error is 5. So 125 minus 110 over 5, right? Well, that comes up with a t-score of 3. Okay, interestingly enough, I postulated that before, but we actually calculated 5 before. So my t-score is 3. Okay, so now problem here is that t-scores are dependent on the sample size, right? So I have to go to my t-table, and I go over here, and for my sample size of 25 again, the t-score that represents 5% chance of being wrong is 2.06. So if I get a t-value that's bigger than this, right? Meaning that the number of standard errors apart that these two values are. If these two values are further apart, I get a bigger t-score in my calculation. If that t-score exceeds 2.06, I know that there's less than 5% chance. There's less than 5% chance that these are from the same population. If my t-score, so in other words, if my t-score is 3, I reject my null hypothesis and I accept my alternative hypothesis. Okay, had my t-score been, say, 1.5, right? If my t-score was 1.5 and I went to this table, I would realize that I haven't achieved the t-value. I haven't achieved a big enough difference between these two values, my sample mean and my comparative population mean. I haven't achieved a big enough t-score to say that there's less than 5% chance of being wrong. And sample size determines how big a t-score you need. So in other words, if I got a t-score of 2.1, right? If that was a sample size of 18 or larger, I could reject the null hypothesis. If it was a sample size of 15 or 14 or 15, I wouldn't be able to reject the null hypothesis because I would not have been able to, I didn't exceed the critical value of t that I would have needed to reject the null hypothesis. Okay, so that's how we would use this. That's how we use t and z in this situation. We're applying the same kind of logic that we did in calculating confidence intervals, except that we introduced the idea of comparing two values to each other, a known population mean to a sample population to find out how far they were apart, instead of using the t or the z score to produce a confidence interval. Similar process, right? Okay, so I'm just going to take a quick glance over here. How are we doing so far? Have I lost you guys? Are you comfortable with this? Okay, okay. You can still hear me, right? We're still clear? Okay, good, excellent. Just wanted to check. Let me make sure we're still recording. We sure are. Okay, so now let's take this to the next step. The next step might be, well, very frequently, we don't know any of the population values. We don't know what the mean value, say, for cholesterol in New York is versus what it is in New Jersey. So let's say that we wanted to compare the two of them. This time, I'm going to be a little bit more realistic. I'm going to say the first thing we're going to do is we're going to establish our null and our alternative hypotheses. Okay, our null hypothesis is that the mean cholesterol for New York is equal to the mean cholesterol for New Jersey. An alternative hypothesis is the mean cholesterol for New York does not equal the mean cholesterol for New Jersey. Okay, so now there's two things about this that I'd like to point out. One is that we don't actually know the means, and we're not going to know the means for either one of them. So we're going to have to rely on two samples, sample from New Jersey, a sample from New York, to determine these probabilities. Okay, so let's think about this. Now, notice I didn't say that the mean for New York is larger than the mean for New Jersey. I said that they were equal, and that we want to prove that they're not equal. So this is what we call a two-sided test. Okay, it's two-sided test because we're not prejudging whether one is larger than the other. We just want to prove that they're different. Okay, so in a two-sided test, that's the situation where we're always going to use. Let's say if we want to be 95% certain, in other words, have a probability of error alpha equals 0.05 or less, that we're going to split up our chance of error, but at the low that New York is lower than New Jersey, 2.5% there, or New York is higher than New Jersey, for instance, 2.5% at that end. So this is a much more rigorous test than saying, oh, I'm going to assume that one is lower than the other, so I don't have to worry about the higher end. I'll put all 5% over here. So my z-score or my t-score can be a smaller number than it would have to be in order to reject the null hypothesis. Okay, so this is going to be a two-sided test. Okay, so let's say we have our two samples. Okay, and one sample has a mean of 100, say 180. That's New York. New Jersey has a mean of 200 in our sample, of course, and our sample size is equal to 100. Okay, standard deviation that we get from these two happens to be very similar. Okay, and let's see. In fact, you know what I'm going to do? You know what I'm going to do? I'm going to start off by making the assumption that the standard deviation for these two populations, maybe for the entire United States, is already known because there have been so many studies. And I'm going to say that the standard deviation for these populations is, let's pick a good number here, by 10 is equal to, let's say 15. No, 15, see. Well, that's not going to be so good. I'm looking for a number that would work well here. I'm going to change these. I'm going to change sample size here to 36. Okay, and I'm going to make my standard deviations 6. Over 6, 10. It's going to be an odd number, but keep in mind that these are fake numbers I'm making up. Let's say my standard deviation is equal to 60. Okay, so now my standard error for these two populations is going to be equal to, assume it's the same for both and that it's equal to 60. My standard error is going to be equal to my standard deviation, which is 60, over the square root of the sample size, which is 36. So 6 into 60, my standard error is going to be equal to 10. Okay, so now, since I know my standard deviation of my population, I can use a z-test instead of a t-test. So my z-score is going to be equal to the difference between the two populations, x1 minus x2, right? New York minus New Jersey, over the standard error, which is equal to, we just calculated, was equal to 10. So what do I get here? I get z is equal to 180 minus 200 over 10 is equal to minus 2.0. Okay, it doesn't matter if we're plus or minus, so we're talking about this end or the other end of the normal distribution. Well, we know for a z-score of 2.0, I can go to my z-table and look up what the area is in that little end of the normal distribution. In other words, what is the area in the tail at a z-score of minus 2.0? What is that area there? Okay, so I'm going to get my t-table, my z-table out. Okay, I have to get this is open. Let me see if I can't get to it. Here we go. Z-table. Okay, so my z-score in the area of that curve for a z-score of 2.0 is 2.0. It's going to be 2.023 roughly. So I'm going to move this out of the way. So the probability associated with that z-score is equal to 0.023. Okay, that's my p-value in there is equal to 0.023. Well, I said my alpha is 0.05. That's the amount of error that I'm willing to accept. Well, 2.3% of the time in this situation, I might get samples that suggest that these are part of the same population, not different, but part of the same population. So if I want my alpha to be greater than what my p-value. I want less than a 5% chance of being wrong. So I want my p-value less than 5%. So I calculated that the area here is 0.023. However, I'm not done yet, am I? What do you think I need to do to this p-value in order to make sure that I have the right value? What have I forgotten to do here? Yeah, Sarika is correct. I would have to double the value for for the true p-value, because I have to account for the upper end, the z-score of plus 2.0, as well as z-score of minus 2.0. So I multiply that by 2, so my p-value is equal to 0.046. So that means I have a 4.6% chance of being wrong if I reject my null hypothesis. Well, anything less than 5% chance of being wrong is acceptable to me. So as long as my p is less than my alpha, I reject the null hypothesis and I accept the alternative hypothesis. Let me just take a quick look at the questions here. Okay. Yeah. You don't double the value of t, you double the value of p that you found, right? Okay. Now, I'm sorry, I didn't use t here, did I? I used z, because why did I use z here? Anybody want to hazard a guess of why I used z to calculate this and went to the z table? Okay, we all understand the reason why I used z is because I knew the population standard deviations. If I don't know the population standard deviations, I have to use the t table, correct? So now let's, for a moment, say that I didn't know the value of the population standard deviation, right? I have a two sample t-test here, and I don't know the population standard deviation. I have to rely on what I calculate is the sample standard deviations, the sample standard deviation for New York and the sample standard deviation for New Jersey. Okay, that's another situation, isn't it? Right? Since I don't know that, I have to use a t-test. Okay, now it's a t-test where I have two different variability, where I have two different variabilities for these two populations. Now, there's two possibilities here, aren't there? Once I get into this situation, the standard deviation in New York may be similar or the same as the standard deviation of New Jersey, or they may be different, right? So now I have to take a fork in the road. There's two possibilities here for my two sample t-test. One is the standard deviations are the same, and the other is that the standard deviations are different. Okay, so now I'm going to have to broach that. I'm going to use an example that we had in the homework in order to approach that. Okay, let me see if I can't find it real quick. Let's see if I can't get this stuff to go away. Let's see. Okay, here's a good one. Okay, this is from homework number 5, which is not due until next week, but has examples of material that could be on the homework, it could be on the test. But you don't have to hand it in. You want to practice it, but you don't have to hand it in right away. So homework number 5, did I just minimize that? Okay, here we go. Here's a situation where we have two groups. One has 23 women. The other one has 24 women. One group got a drug, the other group got a placebo. The mean blood pressure in the drug group was 111. The mean blood pressure in the placebo group was 109. I'm going to change that slightly so that the mean blood pressure is in our problem is, or standard deviation in our problem is 10. Kind of force you to do it again on your own for homework. Okay, and we're going to solve this problem. Okay, so now, just like before, just as we did before, we are going to compare these two groups. Well, we're going to, instead of z, we're going to use t is equal to the mean 1 minus mean 2 over the standard error. Okay, so now I have to calculate what the standard error is. This represents the standard error. Okay, so now you'll notice that we have kind of an unusual formula down here for the standard error. Okay, let me pull up a piece of paper here. Just to answer a quick question. The t-table already gives you, doesn't actually give you a p-value, does it? The t-table actually gives you a value that you have to exceed. So if you go up here and look, you already see it's already saying, well, the t-value is the right tail probability is 0.025. So that's what you need for a 95% confidence interval. It's already taking care of that for you, right? So the only thing is that if you think carefully about this, you could say to yourself, well, what if it's a t-test and it's only a single-sided t-test? You already know it has to be bigger or larger, so your alternative hypothesis is that mean 1 is greater than mean 2, right? So how would you approach that? Well, then what you would do is you would use this t-score for the same sample size as you would use this t-score for a double-sided test. So for a sample size of 17 or 16 degrees of freedom, you're for a one-sided test at alpha equals 0.05, the t that you would have to exceed is 1.7. For a two-sided test, which is almost always what you're going to be running, you would have to exceed 2.12. Okay, so now that you're using that number, that t-score doesn't give you a specific p-value the way a z-table does. Z-table is very nice, gives you a specific p-value, at least for one side of the curve, which you have to double to get for a double-sided test. Now, what you can do with the t-test, if you want to be especially tricky, is you can say to yourself, well, for 16 degrees of freedom, if my t-value that I calculate comes out to be 2.2, I've exceeded what I need, so I can reject the null hypothesis. But I also know that my p-value is my confidence, or my p-value is between 95% and 98% because I didn't exceed what I need for 2.8. If if my t-score I calculate is 3.1, I know that my p-value is between 99 and 98, confidence of 90 and 98, or a p-score of 0.01 to 0.002, right? So it's between these two values. So you can kind of use the t-table to kind of get a range for what your p-value is, but for most of the time, you're just using the t-table to predict whether or not you can reject the null hypothesis at an alpha of 0.05, which is represented by a 95% level of confidence, right? Or a right tail probability of 0.025 plus the left tail of 0.025 added together. Okay, does that help a little bit? Sarika, does that? Okay, good. I'm glad it helped a little bit. Okay, so now I'm going to go back to this calculation, and I'm looking here, and let me get a fresh page. Okay, so now my situation here is that I have two samples. I have two samples. I have x bar one, x bar 1, x bar 2, right? So I'm going to subtract one from the other to get my what my t-score is. I'm going to just assume t from now on, unless I can assume differently, and we'll see if we can or not. Okay, so I'm going to take a look at this, and my t-score is equal to x bar 1 minus x bar 2 over my standard error. Well, when I have two different samples, I have two different standard deviations, right? I got standard deviation 1 and standard deviation 2 from these two samples, because I don't know either population, do I? So now, in order to calculate my standard error, I have a new formula that I'm going to use. And that formula is first going to ask me to calculate a combined standard error for these two. Well, that's called a pooled standard deviation. That's called a pooled standard deviation, combined standard deviation for the two of these. It's kind of a weighted average of the two of them. Okay, so now I calculate that using this formula. Now, before I do that, I can use this formula if I can assume that it's likely that the standard deviations of the two populations are approximately equal. Well, approximately, in this case, they're literally equal, right? They're 10 and 10. A lot of cases might be 10 and 12 and so on and so. Very rarely would they be exactly equal. Okay, so at what point do I say to myself, they're not equal? Well, typically, as long as one standard deviation is not twice the other standard deviation, you can use this logic in combining the two standard deviations. Assume equal variances for these two populations. 10 and 12 would be fine. 9 and 7 would be fine. 10 and 15 would not be fine. You would not assume equal standard deviations for the two populations. Okay, so that would involve another formula. For our purposes, in this case, we're going to calculate the pooled standard deviation. And I'm not going to actually do the calculation to save time, but just to give you an idea, okay, N1 is your drug group, N2 is your placebo group. So this would be 23 minus 1 or 22 times 10 plus N2 would be the sample size 24 minus 1 is 23 times my standard deviation squared, which would be 10 squared in this case because that's my placebo group. They might be S1 squared, S2 squared might be different numbers, given but likely be different numbers in a real life example, right? Divide that by the sample size, the two sample sizes combined minus 2, or in other words, n minus 1 plus n minus 1, n2 minus 1, right? And you would resolve that. In this case, as a matter of fact, I know since this is 10 and this is 10, this pooled standard deviation is going to become 10. My pooled standard deviation goes into my t calculation. X bar minus x bar 2 is going to be 111 minus 110 is going to be 2, divided by the square root of the pooled standard deviation, which I know is going to come out to be 10 just because they're both the same. That, again, a very unusual situation. So what's my t is going to be equal to 111 minus 109 over, let's see, the square root of my pooled standard deviation is 10. So that squared is 100 times 1 over n plus 1 and 1 over 23 plus 1 over 24. Okay, so what's that going to be equal to? I'm going to get my calculator out. And it's going to be equal to, let's see, 1. Let me clear everything out here. Make sure I got nothing in my memory. 1 over 24. 1 over 23 I'll start with. Is equal to that. I'm going to put that into memory. And clear. 1 over 24 is equal to this. I'll add the two of them together. And that's what I wind up with. I'm going to multiply them by 10 squared, my pooled standard deviation squared, times 100. I think I clicked that already, right? Oops, did I do that right? I'm going to clear this. I'm going to do it again. 1 divided by 24 equals that. I'm going to add those two together, times 100. Yeah, I screwed things up a little bit there. Okay, comes out to that. And I'm going to find the square root of that number. Square root of that number is approximately 3. So my t value is going to be equal to approximately 2 divided by 3. Okay, so that comes out to be 2 divided by 3 is 0.66 or 0.67. So my t-score is 0.67. I really don't even have to go there. I know I have not exceeded the p-value that I need to reject the null hypothesis, which were, now what sample size do I use? My sample size, my degrees of freedom is equal to n1 plus n2 minus 2. Okay, that's equal to 23, 47 is equal to 45. So I could go to my t-table for 45. Okay, I'm going to be conservative, stick with 40. And I needed to exceed a t-value of 2.02. I failed to exceed that critical t-value, so I failed to reject my null hypothesis. Remember, my null hypothesis, since this is a two-sided test, was that mu1 is equal to the mean blood pressure of the drug group is equal to mean for the placebo group. Okay, and our alternative is that they're not equal. Okay, now since I failed to reject my null hypothesis, right? I failed to reject my null hypothesis. I don't say that I accept my null hypothesis. I say that I failed to reject it. We didn't prove that they're equal. We just failed to prove that they're not equal. Okay, so so that's how we would use that. Now I think I changed that. I think it was 8 and 8 before. So you're going to get a different answer on the homework than I got here. Uh, uh, um, and but you'll actually have to run through the example itself. Okay, I hope